Welcome to the last part of our lecture entitled Mass as Triple Integrals in Rectangular Coordinates. So we'll just be doing some exercises uh, concerning the lesson that we have just studied. So here we will just study the first and the second one, and I will leave the last one to your discussion teacher. So the first question is find the mass of the solid, and we see that it's a triple product. No, it's a Cartesian product of three intervals, so it's a rectangular box whose density function is xy plus z squared at any point xy z. So the mass, by definition, is just the triple integral over the solid of xy plus z squared dv, and uh, because it's a rectangular box, there's no problem about how you change your dv. So I chose the most natural permutation, so it's just dx dy dz, and I have to make sure that the variables correspond to the limits of integration. So for instance, the innermost integral is with respect to x. I know the interval corresponding to x is 0 to, so that means that the innermost limits of integration will also be 0 to. So I do that as well for y and z, and I get this integral. And I hope you got this because this is the most important part in setting up the triple integral. Because after this one, you will just have to evaluate as you do with double integrals and so on. So now we treat the innermost integral, so we're integrating with respect to x. Y is constant, so integral of x is x squared over 2. I'm just gonna copy y. Integral of z squared is just xz squared, and then I evaluate from 0 to 2. Sometimes I put x equals 0 just to emphasize that, or to remind myself that I'm integrating or I'm evaluating with respect to x. So now I evaluate x equals 2, I get 2y, and here I get 2z squared. When x equals 0, everything goes away. Now I do that as well for y, and I get this function, and with respect to z, I get z plus 2z cubed over 3. Evaluating through the limits of integration, I get 21. No? It's 3 plus, this is 9, 9 times 2 is 18, 18 plus 3 is 21. When z equals 0, everything goes away, so the final answer is 21. Okay, so the next problem is to evaluate the triple integral, this one where G is the tetrahedron. So a tetrahedron is basically a pyramid. No? Enclosed, tetrahedron is a pyramid whose base is a triangle. Enclosed by the three coordinate planes, that's x equals 0, y equals 0, and z equals 0, and the plane 2x minus 3y minus z equals 6. So I hope you remember how to draw the planes. So you just have to look at the intercepts, no? So when y and z are 0, then you get the x-intercept, which is equal to 3. And when x and z are 0, then you get the y-intercept, which is equal to minus 2. And finally, the z-intercept is equal to minus 6. So you draw this solid and you get your tetrahedron. Okay? So the tetrahedron is in this part, it's not in the first octant. And sometimes it becomes disconcerting because it's not in the first octant, but you might as well know how to address those kinds of solids if it comes up with an exam or a particular situation that we need to evaluate this integral. So now let's verify that this is indeed a solid of type xy. So do we have a projection onto the xy plane? Yes, the projection onto the xy plane is nothing but this triangle. And if we zoom it here, so it's just an xy plane, and the x-intercept is 3. Remember, this is the x-axis. So this is 3. The y-intercept is minus 2. Okay? And so this is your projection, and on all the points of the on the projection, do you see a well-defined roof and floor functions? Yes, the floor has as equation z equals 2x minus 3y minus 6, which is just the one that's given here. Okay, and then the roof function is nothing but the xy plane, which has equation z equals 0. So now the triple integral is nothing but the double integral over the projection r dA, and the integrand is just the single integral of the elevation dimension. So the single integral of x plus 2y dz, and then the floor function becomes the lower limit of integration, and the roof function is the upper limit of integration. Okay, so now because R here is already drawn, we might as well know what the limits of integration here are. And you know why here, if you draw a vertical strip, you have the top and bottom functions. The top function is certainly the x-axis, which is equation y equals 0. And the bottom function is y equals 2x minus 6 over 3. And where did I get that? I got that from this. Because remember that this is the plane 2x minus 3y minus z equals 6. So this line is the intersection between this plane and this plane, right? So I'm just going to make z equals 0 because I'm intersecting these two planes. So when I make z equals 0, you get 2x minus 3y equals 6, which is just this. So if I isolate y over here, y is equal to 6 minus 2x over minus 3, or 2x minus 6 over 3. That's why this is the bottom function and this is the top function. Okay? And clearly, x here ranges from 0 to 3. So now we look at this triple integral now. So integral from 0 to 3 with respect to x, integral from 2x minus 6 over 3 to 0 with respect to y, and integral from 2x minus 3y minus 6 to 0 with respect to z. Okay, so remember, we look at the innermost integral and do the evaluation there first. Remember that has no z, so this is treated as constant with respect to z. So the integral is just you copy that one and then you multiply by z, and then you evaluate from 2x minus 3y minus 6 to 0. And when z equals 0, everything becomes 0. Subtract it with the evaluation when z is equal to this. So you get x plus 2y plus 2x minus 3y minus 6. I did the computation over here. So if I evaluated everything, I will get this. Okay? And then the minus sign I put outside of the integral. And I'm just gonna give you a warning. So I tried this a while ago and it gave me very cumbersome computations. And we will see later with a very simple example that even with the simplest example, if you're treating tetrahedrons, you get very cumbersome computations. So I did a little Wolfram alpha, some cheating with Wolfram alpha, and after a lot of computations, it just gave me minus 1.5. So just to give you an idea how it could become cumbersome with a very simple example, this is a full solution of this problem. So what is the mass of the tetrahedron in the first octant bounded by x plus y plus z equals 1? And the density is simple also, it's y plus 2z. It's very easy to draw this tetrahedron. Remember that we are in the first octant, so I'm just gonna draw this x, y, and z axes, and then I'm also gonna draw this plane, no, which has x, y, and z intercepts all equal to 1. So everything is really simple over here. And remember that this is clearly a solid of type xy because the projection is this triangle. And we can see that the roof function is nothing but this plane over here. And the floor function is this xy plane, which is z equals 0. So I'm just going to label here, this is z equals 0, which is your floor. And this is z equals 1 minus x minus y, which is your roof or ceiling function, right? So this is clearly solid of type xy. So you see here that I wrote the mass or the triple integral as a double and a single integral. The single integral is from 0, which is the floor function, to 1 minus x minus y, which is the ceiling function of the same integrand, which is your density function, and then dz dA. So now I'm gonna skip first writing the limits of integration with respect to r. I'm gonna try and simplify this. Okay, so I will evaluate this with respect to z, the integral of that with respect to z. So y is constant with respect to z, the integral becomes y z. 2z, the integral of that is z squared. And then when you evaluate from 0 to 1 minus x minus y, you get y times that one plus the square of 1 minus x minus y. Thankfully, when z equals 0, everything goes away. And then if I factor 1 minus x minus y out, I get that one times y, which is the one left out in the first term, plus one of these. So you get y plus 1 minus x minus y. You see the y's go out. So I just have 1 minus x minus y times 1 minus x. So just to facilitate everything, what I do is because I'm thinking that I'm gonna integrate with respect to y next. So this has no y, so I multiply this to 1 minus x. This is constant. These are constants with respect to y, and then minus y I multiply to 1 minus x as well. So that's why I get this expression. And now I look at the R, which is the projection onto the XY plane. I stick out a vertical strip and look at which function is the bottom function and the top function. The bottom function is clearly the x-axis, which is y equals 0. The top function is clearly this x plus y equals 1, which is this one when z equals 0, because remember that this one is the intersection of this plane and the z equals 0 plane. So just put in z equals 0 here and you get the equation of this line. So you get y equals 1 minus x. This is a restatement of this one. That is your top function. And clearly when x ranges from 0 to 1. Okay? So now this becomes dy dx, and y and x are ranged through these functions. So you see the integral of this same function over r, you get 0 to 1, 0 to 1 minus x of this one. And we are integrating respect to y. This has no y, so this is constant with respect to y. Y here becomes y squared over 2. After evaluating from 0 to 1 minus x, you get something like that. So this one minus half it equals half it. So the 1/2 I got out of the integral, and you have 1 minus x cubed. I don't want to expand this, so I just did some substitution, and after doing everything, I got 1 over 8 as the final answer. So this final example just gives you the most or the simplest a problem, and yet it's quite cumbersome because you're doing an integration over uh, a tetrahedron. Okay, so yeah, I just added this one because I felt bad that I cheated with Wolfram Alpha. Okay, so this is the last part of this lecture. Hope you got some lessons, and we will continue with more discussions about triple integrals. So, for instance, what about solids of type YZ, solids of type XZ? But in our discussions, in our further discussions, because this is quite abbreviated because of the pandemic, we will almost always just consider solids of type XY, no? Because it's quite natural to project onto the XY plane. Okay, so this ends the lecture. See you in the next lecture.